Hi everyone. My name is Dr. Kalogirou, and I am an assistant professor in the School of Mathematical Sciences. Before I start giving this lecture, which will be a taster lecture on calculus, I would like to say a few things about myself. My role in the School of Mathematical Sciences is to do research and teaching mainly. My research is on the field of fluid mechanics, which means that I'm interested in studying how fluids move. And by fluids, we usually mean liquids or gases. As I said, I'm also teaching in the school, mainly applied mathematics modules. And I also hold the role of careers and internships officer. And as part of that role, I am mainly responsible for helping our undergraduates and postgraduate students with careers and organizing relevant events. And also I coordinate the summer research internships, which take place every year in the school. So that's briefly about me. Now let's start with our lecture. So this lecture will give you a taste of what a university lecture is like. And in particular, the topic we will be looking at today will be calculus, which is one of our core first-year modules. In particular, the topic of this lecture will be on ordinary differential equations. So during this lecture, you will have the opportunity to participate in a few polls and some quizzes. And the questions in the quizzes will be based on the topics that I will be presenting. You can participate in the polls and the quizzes by either using your computer or mobile device. You can use your mobile phone's camera to scan the QR code, which will be given on the quiz slide. A QR code looks like this, and you can scan this and then access the quiz. Or you can also click the link which will be provided in the Teams Q&A chat. So before we start with introducing the topic of this lecture, we will begin by looking at some basic ideas which will be needed in order to understand the lecture. So the main knowledge that you should have before looking into ordinary differential equations, which is our topic today, it's about the derivative of a function. So in particular, the derivative is defined as shown here. If we have a function, let's say y of x, we denote the first derivative of this function with respect to this variable x by writing dy dx. And below here on this slide, I'm showing some of the most well-known or most famous derivatives of functions. And we will go through these one by one. The first derivative that we have here, it's one of a power, and that is if we take d dx of a function x to the power of a, then the derivative is just simply the power gets in front of x as a coefficient, and then the power. The derivative of an exponential function e to the power of x remains the same and unchanged. We can also define the derivative d dx of the sine and the cosine functions, and similarly of other trigonometric functions, as you can see here. And once we have defined and calculated the first derivative of the function, we can then continue to find higher order derivatives, such as the second derivative. And this can be found by taking the derivative of the first derivative. For example, if we consider our power x to a, and we want to find the second derivative of this is equal to the first derivative of the derivative, which we have found above. And the calculation, then it's similar to before. We get the power appearing in front as a coefficient, and then the power then reduces by 1. The second derivative of an exponential can be found by taking the coefficient of x in front of the exponential, and this is raised to the power of the derivative times the exponential function. And similarly, we can extend this to derivatives of higher order dn dxn, where n is an integer, can be 1, 2, 3 or higher, of an exponential, for example. In this case, we get b to this power of n times our exponential function. Before we move on, I would like to clarify the notation that we will be using, not only in this lecture today, but in general in mathematics. When we use derivatives, we can use different notation to denote the derivative. So for the first derivative, we have seen above that we can write dy dx to denote the first derivative of function y with respect to x. But we can use different symbols to denote the function, and different symbols sometimes to denote the independent variable to which this function depends. For example, if we have a function f of x, we can also write the first derivative as d dx of this function. If we have the function g that depends on r, another notation of the first derivative is to use the prime notation. 1 prime corresponds to 1 derivative, 2 primes to 2 derivatives, and so on. And finally, there's another notation that it's mostly used in physics, in cases where we have a function that depends on t, and in physical terms, this t corresponds to time, and usually x is the function, and this corresponds to displacement. And the dot notation is used in that case, where 1 dot, it's the first derivative, 2 dots, 2 derivatives, and so on. So the first derivative in this case will be the speed, and second derivative will be the acceleration of the body. Now let's move on to define what is an ordinary differential equation. Differential equations in general involve unknown functions and their derivatives. And when we say that we have an ordinary differential equation, which is also called simply ODE, where O, D, and E come from the first letters in ordinary differential equation. This is an equation that involves one unknown function that depends on one independent variable, and it can also involve derivatives of this function up to some finite order, which will be known. It would be an integer order of the derivative. For example, simply we see below, an ODE, it's an equation that involves a function, let's say y of x, and can involve the derivatives of the function, not necessarily all of the derivatives, but up to some order, and it can involve some or all of these derivatives. So here we can see two examples of ordinary differential equations, and both of these examples shown here are both ODEs where the unknown function is y and the independent variable is x. We can see this because we see function y and derivatives of this function appearing in both equations, and we see also this dependence on x, which is the independent variable here. For the first ordinary differential equation, a solution is given by this expression. We will not go through the details of how to obtain this solution in this lecture, but just as an indication of what the solution looks like, this is the exponential of x squared. And you can try later at your own time to take the first derivative of this function and then substitute here, and also substitute the right-hand side and confirm that indeed this expression is a solution of this ordinary differential equation. And similarly, for the second ODE we have on this slide, this is one solution that you can verify later if you take the derivative, first and second derivative, and substitute here. You should be able to confirm that it's a solution. So the task we have when we are given an ordinary differential equation is to solve this and find the solution. But before we do that, and in order to choose the right solution method, we need to first classify ordinary differential equations, and we can classify them into different categories according to their general characteristics. The first thing we should be doing is first we need to identify the independent and dependent variables, and here we have two examples where we would do this. In the first ordinary differential equation we have here, we can see that this involves unknown function y and its derivatives. And Also, we have dependence on x. So y here is the dependent variable and x is the independent variable. In the second example, we have, remember this x dot notation. It appears in the case where we have an unknown function that depends on time, or t here. And we can see, because we have derivatives of this function x, that this is our unknown function here. So the dependent variable in this differential equation is x, and the independent variable is t. Okay, so time for a quiz now. The question that I would like you to answer is, how many ordinary differential equations do you see on this slide? You can access the quiz by either scanning this QR code using your phone, or going to this link and using this 8-digit code, or you can also find the link of the quiz in the chat box. So think about how many ordinary differential equations you see here, and in particular, how many distinct ODEs do you see? I'll give you 1 minute or two to think about it and vote in the quiz, and then we can see the answer together. Okay, I hope that you'll have the chance to vote and submit your answer to the quiz. Let's now have a look at the solution of this exercise. So first, we look at the first two equations we see on this slide. We can identify that both of these equations have a known function y of x that depends on x, because we see here this prime notation and here derivatives d squared y dx squared. And remember the notation that I mentioned at the beginning of the talk, that y prime is the same as dy dx, y double prime is the same as d squared y dx squared. So we can conclude that both of these equations are essentially the same ODE. Now, looking at the last two equations, here, if we remember the notation and the remark I made before about this dot notation, the unknown function in both of these equations is x of t, because x dot is dx dt and x double dot is the second derivative with respect to t. And therefore, we can also conclude that both of these equations are the same ODE. However, if we compare all of this together, we can notice that the coefficients that appear in front of the unknown function in each case and the derivatives are actually the same. So here we can conclude that we have the same ODE in all four equations, and it's the same ODE, but just appearing in four different forms. So the answer to the question of how many ODEs or distinct ODEs we see here, it's that there's only one. Now let's continue with the classification of ordinary differential equations. The next property we will see is the order. So the order of an ordinary differential equation is the highest derivative that appears in the equation. And here we will see some examples. In the first ODE we have here, we can see that the highest derivative is this second derivative, and therefore the equation is of second order. In the second example, the highest derivative is the first derivative, so this is a first order ODE. And in the last example below, we have the highest derivative being here, the fourth derivative, and therefore this is a fourth order ODE. The next property we will look at is the degree of an ordinary differential equation, and this is defined as the power to which the highest order derivative is raised. But note that in order to find this power and the degree, we need to first rationalize the equation to contain only positive integer powers of derivatives. So now let's look at some examples. The first example we have here, we need to find the degree of this equation. Firstly, we need to identify what is the highest order derivative that appears in this equation. This is clearly the fourth order derivative, so it's a fourth order ODE. And we see that this is raised to the power of 2, so this is of second degree. Let's see now another example. The highest derivative here is the second derivative, so this is a second order differential equation. And to find the degree, we need to see at what power is this raised. But remember, I have said already that we shouldn't have any fractional powers in this equation when either the unknown functions or any of the derivatives are raised to a fractional power. We need to first rationalize the equation and then find the degree. So how can we do that for this example? We can rewrite our ordinary differential equation by keeping this term with the fractional power on one side and then taking all the other terms on the other side of the equal sign. Notice that these will take a minus. And then we can raise both sides, left and right, to the power of 4. And therefore, we have first derivative to the power of 7 here, and then all these right-hand side terms to the power of 4. And now we have no fractional powers in the equation. So now we're able to find the degree of this equation. Remember, we have seen already that the highest order derivative is the second order. And this is now raised to the power of 4, so the degree is 4. Now it's time for another quiz. On this slide, you can see 3 different ordinary differential equations. And if you scan this QR code or click on the link that you can find in the Q&A chat box, you will find some questions that are asking you about the order and the degree of these ODEs. So try to answer these questions. You have about 1 or 2 minutes, and then we will be back to have a look at the solutions. Okay, I hope that you have the chance to answer the questions of this quiz. Now let's look at the answers. So the first ODE we have here, we need to find its order. We see that the highest derivative that appears in this ODE is the first derivative, so it's a first order. And this is raised to the power of 3, so the degree is 3. In the second example, we have the third derivative being the highest, so it's a third order ODE. This is raised to the power of 1, so the degree is 1. And in the third equation, we have the second derivative being the highest derivative that appears, and this is raised to the power of 2, so the degree here is 2. Let's continue now with the classification, and now we will look at the property of linearity. So in general, a linear ordinary differential equation of order n, where n is an integer, has this general form, where here we assume that our unknown function is y, and this depends on variable x. And by writing this form for a linear ODE, this means that we have the unknown function y and its derivatives appearing linearly. And that is that all these derivatives and the function itself are only raised to the power of 1 or 0 if we have some terms missing, and are not multiplied together. If any of these two properties are not satisfied, so if we have some derivative or the function itself raised to a higher power than 1, or terms multiplying each other, or any other term that it's not linear, then we say that the ordinary differential equation it's non-linear if it's not linear. So let's see now some examples of where we will be able to see if these ODs shown here will be whether they are linear or non-linear. In the first example, we see that all the derivatives and the function itself appear linearly. They are raised to the power of 1, so this is a linear OD. In the example below, we notice that one of the derivatives is raised to the power of 3, so this has to be a non-linear OD. Here in this example, again, the function and the derivative appear to be raised at the power of 1, so this is a linear OD. Here we see the function of y and the derivative being multiplied together, so this is non-linear. And in the final example, we see an exponential raised to our unknown function y, so this is clearly now non-linear. A remark here is that while we have the requirement of the unknown function and derivatives appearing linearly, the coefficients of these terms, which are generally functions of x, which is the independent variable, these can be nonlinear in x. And we have seen this in one of our examples where we had an x cubed term, but this didn't affect the fact that the equation was linear. So to decide if an OD is linear or not, we only need to look at the unknown function and its derivatives. So the final property we will see today has to do about an ODE being homogeneous, and in particular about linear ODE. So this property only applies to linear ordinary differential equations that have the general form that we have seen before on the previous slide. Now we're interested in whether this equation has a non-zero right-hand side. So this equation is said to be homogeneous if and only if the right-hand side function f of x vanishes identical. So if the function on the right-hand side, which only depends on x, is 0 for all values of x, then the equation is homogeneous. And if it's non-zero for some value of x, then we say that it's inhomogeneous. Note here that to find this right-hand side function, we need to take to the right-hand side all the functions that depend on x, and keep on the left-hand side everything that involves y and its derivatives. So we have here two examples. In the first case, this is clearly a linear OD, and we see that it has a 0 right-hand side, so this is homogeneous. And then in the second example, again, same linear OD on the left, but it has a non-zero right-hand side. So this is an inhomogeneous linear ordinary differential equation. Okay, so time for our next quiz. You can see on this slide 3 different ordinary differential equations, and you can scan this QR code or access the link from the chat to answer some questions about whether these equations are linear, nonlinear, homogeneous, or inhomogeneous. So you'll have a couple of minutes to answer these questions, and then we can look at the solutions together. Okay, I hope you all had the chance to answer the questions in the quiz. Let's have a look at the solutions now. The first ODE we have here, it's clearly nonlinear because we have the first derivative raised to the power of 3. So if you remember the definition of a linear and a nonlinear ODE, this is what satisfies, this is clearly nonlinear. The question in the quiz was also asking whether this was homogeneous or not. However, if you remember the definition of an ordinary differential equation being homogeneous, this was only referring to linear ODEs. So here, because we have a nonlinear ODE, we cannot say anything about whether this is homogeneous or not. So that's the only answer that's correct for this first question. For the second ordinary differential equation, we can see that this is linear because the unknown function and its derivatives appear to be raised to the power of 1. And then we have a non-zero right-hand side that depends on x only. So it's an inhomogeneous linear ODE. And the third example, it's again a linear ODE because the derivatives here appear to be at the power of 1. And we see that this term only depends on x. So it should be taken to the right-hand side, as I explained on the previous slide, and therefore this equation will be inhomogeneous. So that's all I wanted to say about some basic properties of ordinary differential equations in this taster lecture. But before we finish, I would like to discuss briefly about some real-life examples of ordinary differential equations. So it's important in the study of ordinary differential equations. It's very important in many applications. And here we see the first example, which is the motion of it's a simple harmonic motion. For example, if we have a harmonic oscillator consisting of a weight attached to one end of a spring and whose other end is connected to a wall, then the motion of this weight can be described by this second order ordinary differential equation, where x here denotes the displacement of this body, m is the mass, and k is some constant. And remember, this double dot is the second derivative. We can use this equation to model also other phenomena that follow a simple harmonic motion. For example, the motion of a simple pendulum, as shown in this sketch. But in this case, The x in the equation denotes the angle that the pendulum creates with the vertical. Another example where ordinary differential equations are useful is to describe a ball's trajectory in football. In this case, an ordinary differential equation that can be used is shown here in this box, where you might notice that x and f in this equation are written in boldface. What this means in mathematics is that both of these quantities are vectors, which means that they depend on more than one variables in space. So here, x of t, it's a three-dimensional vector that has three components and describes the position of a ball in three-dimensional space. M is the mass of the ball, and the right-hand side function f of t can depend on the displacement and its derivatives, and generally represents the forces acting on the ball due to gravity, drag, or lift forces. And the final example that I would like to mention is that we can use ordinary differential equations and our knowledge to solve them in the modeling of the dynamics of an epidemic. There's a lot of models that can be used, and many of them are quite complicated. However, one of the most famous and the simplest models that can be used to model an epidemic is the so-called SIR model. This consists of three ordinary differential equations that depend on three variables, S, I, and R, where S is used to denote a susceptible population to an epidemic. I is the infected population, and R is the removed population, either removed by death or recovery. So the idea is that we have to solve these three equations simultaneously because they're coupled with all these three parameters. And after we do that, we can use information from these coefficients as well to gain understanding also about the basic reproduction number, which is probably a quantity that you heard a lot about these recently in the news. And so this is denoted by R naught, and it's the ratio between these two parameters that appear in this equation, beta over gamma. And if this parameter is found to be greater than 1, then what it means is that the number of infected individuals increases exponentially. And this is not very good news when we have an epidemic. I don't plan to go into more details about this in this lecture, but if you would like to hear more, please attend the popular maths talk on using maths in the fight against COVID-19. This talk will be given on the 6th of May at 5 p.m. and you can scan this QR code, which will take you to the web page that advertises this talk and other talks. So this is the lecture. I would now like to hand over to my colleague, Dr. Joel Feinstein, who will be giving a brief overview of the various maths courses that we offer here at the University of Nottingham. Thank you very much for listening, and if anyone has any questions, please post them in the chat and I will be able to answer later.